Now let's have some understanding of nuclear fusion, and obviously we understand that when two lighter atoms, nuclides fuse together, they form a big nucleus, and in doing so, what happens is energy is released, and this kind of reaction is called as nuclear fusion, and certainly it's a process in which two very lighter nuclei they combine, they fuse to form a nucleus with large mass number, along with simultaneously releasing tremendous amount of energy. And this kind of reaction, we call this kind of process as nuclear fusion. Now, if we take an example of two nuclei of deuterium, H21 plus H21, what we get is He3, 2, and a neutron and Q. And when we have four hydrogen atoms, I mean, when we take four hydrogen atoms, in another example, this is first example, where we have four hydrogen atoms and we fuse them together, and what we get there is helium nucleus, with the with two positrons, uh, and and uh, and and two neutrinos and the Q. So energy released due to the fusion of four hydrogen nuclei, we can calculate that using Einstein's mass energy relationship. So what will be that? That will be mass of four hydrogen atoms, nucleuses, and minus mass of helium, and multiply it with c scat. So taking the values of four into atomic mass units, 1.007825 minus 4.002603 atomic mass units. So atomic mass units, and so to say what we'll get is 0.028697 times 931 mega electron volts, and this value nearly comes out to be 26.7 mega electron volts. So we can have a reaction as four hydrogen nuclides. They fuse, they give us helium, and they give us two positrons, and they give us two neutrinos, and an energy of 26.7 mega electron volts. Now, the process of nuclear fusion can be explained with the concept of binding energy per nucleon, of very lighter nuclei that we have in binding energy curve. And binding energy per nucleon of very light nuclei, we understand, is less than that of the intermediate that we have in binding energy curve. So what it means that light nuclei are less stable, and these light nuclei are less stable than that of intermediate nuclei in the binding energy curve. So this shows that the sum of the masses of the individual nuclei is more than the mass of the nucleus formed by the fusion. So when you have a fusion, you have a heavy nucleus, and there is a difference in mass. This difference is mass in mass is called as mass defect. When this mass is calculated, we are able to calculate the energy. And what we see in this case is that the difference in mass is released in the form of energy. So So release of energy is an indicator of nuclear fusion, and hence this nuclear fusion is an exothermic nuclear reaction. And to say further about is further about this nuclear fusion, we also call it as thermonuclear reaction. So nuclear fusion cannot take place easily. It's not an easy process. I mean, when two light nuclei are brought closer to each other, they exert a repulsive force on each other due to their positive charges. So you bring them close, and they're gonna repel each other. As such, these nuclei cannot fuse together. Thus, these nuclei can fuse together if they have enough kinetic energy with which they to overcome this, by virtue of which they can overcome this repulsive force due to their charges, due to their similar charges. The force of repulsion between them is is large, so it has to be overcome by the energy of these fusing nuclides. So high kinetic energy implies a high temperature. So you need high kinetic energy of the particles, so you want very, very high temperature. Thus nuclear fusion can be achieved at a very high temperature. And that's why what we say, we call it a thermonuclear reaction, because it's dependent on the temperature. You cannot have the fusing of the two lighter atoms at ordinary temperatures. So in fact, this temperature that we need to fuse these two nucleuses, it's of the order of 10 to the power of 8 Kelvin. And this much of temperature is required to trigger a nuclear fusion. This much temperature is available in the core of sun and other stars in the galaxy, in the universe. So nuclear fusion occurs in the sun and other stars in the universe. Now, we would like to have a calculative comparison uh, between nuclear fusion and nuclear fission to have a measurable understanding that in which reaction we produce more energy. Now, to do that, let me consider 1 kilogram of, if I take 1 kilogram of uranium 235 and 92, and this much of uranium will go under nuclear fission reaction. Okay, so to calculate the number of atoms in 1 kilogram, what we will have. So for that, what we need is Avogadro's number. We will have Avogadro's number divided by atomic weight of uranium, and we'll multiply it by the mass, say in grams. So when we do that for Avogadro number 6.023 into 10 to the power of 23, then this will be 10 to the power of 3 grams, taking the atomic weight of uranium 235. And this value comes out to be 2.56 times 10 to the power of 24. So we have this much of atoms in 1 kilogram of uranium 235. Now, since energy released per fission, what is the energy released? Energy released per fission is nearly 200 mega electron volts. So the energy released by this much of atoms will be 2.56 times 10 to the power of 24 times 200 mega electron volts. That will be the case. So this comes out to be 5.12 into 10 to the power of 26 mega electron volts. So this much of energy can be released when we have a nuclear fission of uranium atoms, and if we take 1 kilogram of uranium atoms. Now, let us take 1 kilogram. Now let's go with the nuclear fusion. And certainly this nuclear fusion, it occurs inside the sun. And taking the case of 4 hydrogen atoms, 4 hydrogen nucleuses which fuse together. So you have 4 hydrogen nucleuses. So we are now trying to talk about fusion. They fuse together. And let us find the energy released due to the fusion of 1 kilogram of this hydrogen. So, so to proceed, so what will be the number of atoms in 1 kilogram of hydrogen? Okay, that will be Avogadro's number, 10 to the power of 23 divided by 4, taking 4 hydrogens into consideration, into 10 to the power of 3, and this will give us 1.505 times 10 to the power of 26 number of atoms in 1 kilogram of 4 hydrogen atoms. It is 1 kilogram of 4 hydrogen atoms, because 4 hydrogen atoms take part in fusing together to form helium. Now, now we can calculate the energy released. So what will be the energy released? Because energy released due to one fusion of 4 hydrogen atoms, nuclei, is equal to 26.7 mega electron volt. We have calculated it. So what will be the energy released? So what will be the energy released? Yeah, by 1 kilogram. Okay, during fusion, that will be 1.505 into 10 to the power of 26 times 26.7 mega electron volts, and this comes out to be 40.2 times 10 to the power of 26 mega electron volts. And we can see here that the energy released by fusion, it is 40 times 10 to the power of 26, and the energy released by fission is 5 times 10 to the power of 26. So here we understand that the energy released due to nuclear fusion is large in comparison to the energy released due to nuclear fission.